Hi students, are you ready to learn valence bond theory? Yes. So, do you know who proposed this valence bond theory? Here you can see the famous scientist, the Pauling. He proposed valence bond theory somewhere in 1928. So now let us see the valence bond theory. So now by the end of this video, you are going to see or learn the following. So you will be able to learn the postulates of valence bond theory. You will be able to learn the electronic structure of complexes, hybridization, the shape of the complexes, how to tell about the magnetic properties of the complexes, and finally the drawbacks. So now let us see the postulates of valence bond theory proposed by Pauling. So the postulates are as follows. So for the formation of coordinate covalent bond, central atom will make available the number of empty orbitals equal to its coordination number. So empty orbitals will be equal to its coordination number. So if the coordination number is 4, it will make available the empty orbitals as 4. If it is 6, the empty orbitals will be 6. So each ligand must consist of at least one pair of electrons for donation to form sigma bonds. So if there are 4 ligands, it will donate 4 pairs like that. So the coordinate covalent bond formed when vacant orbital of metal overlaps with filled orbitals of ligands. That is how the coordinate covalent bond is formed. The metal does not take part in hybridization process. So always the metal ion will not participate in hybridization process. That is why they are called as non-bonding metal electrons. From paired and unpaired electrons in the complexes, it is possible to predict the magnetic properties and geometry of the complexes. If the electrons are paired means dia. So 2 means dia. So if the electrons are paired, the complex is said to be diamagnetic. If the electrons are unpaired, it is called, and the magnetic property is paramagnetic in nature. The atomic orbitals of metal may undergo hybridization to form new set of orbitals which overlap more effectively with ligand orbitals, and thus they form strong bond between metal and ligand. So these are all the postulates of valence bond theory, and we can see these postulates by taking the examples. So these are the examples regarding valence bond theory. So now we can see here the example NiCl4. So for this nickel, we are writing the orbital structure. So now nickel atomic number 28. So this is the configuration of nickel. So now here in this complex, the oxidation number of nickel is calculated as 2 here. So plus 2 ions. That is why we are removing 2 electrons. So here we can see, so plus 2 charge means we should remove 2 electrons. So here the configuration happens like this. So now here the 2 electrons are removed in this place. In 4s, the 2 electrons are removed, and this is the configuration of nickel ion. So now how to write the orbital structure, orbital diagram of this Ni2 plus ion. So this is how we are going to write the orbital diagram of nickel ion. So now if you observe here, there are 2 unpaired electrons. So now these are empty orbitals. So 4s and 4p orbitals are empty orbitals, and 4 chlorines, they give a lone pair of electrons each for this vacant orbitals. So now 1s and 3p orbitals participate in hybridization. That is how sp3 hybridization is formed. So here we can observe the pictorial diagram of the complex. So now if you observe here the electrons, so in this complex you can find the unpaired electrons. Here you can observe the unpaired electron, here unpaired electron. So now based on this we can tell the magnetic behavior. So because of the presence of unpaired electrons, the magnetic behavior we can tell this particular complex is paramagnetic in nature. So this structure, the magnetic nature is paramagnetic in nature, and hybridization is sp3 hybridization, and shape is tetrahedral shape. So here tetrahedral shape. So here we can see the diagram representation. So this is 3D diagram, and here this is the diagram what we should write. So this is the example for tetrahedral complexes with sp3 hybridization. So next example, this is also a tetrahedral complex MnCl4 2-. So here manganese atomic number 25, and this is the configuration. So Mn2+. So you should calculate the oxidation state, and it is Mn2+. Here +2 means, so we are removing 2 electrons, and now writing the atomic orbital diagram. So here we can see the vacant orbitals 4s and 4p. So now the ligands are coming and joining these vacant orbitals. You can observe here the 4 chlorine donating 2 electrons each. Now the hybridization here is sp3 hybridization. So now here we can observe the unpaired electrons. So the magnetic property is paramagnetic. So you can for this structure the hybridization you can see as sp3 hybridization. The shape of the molecule tetrahedral, you can observe here the tetrahedral shape, and magnetic property is paramagnetic because of the presence of unpaired electrons. So now we will see the square planar complexes with dsp2 hybridization. So these are the examples. So we are taking nickel. So atomic number of nickel 28. This is the atomic configuration of nickel. So now nickel ion. So nickel ion. So we are removing these 2 electrons, and then here it is written as 0. So now atomic orbital diagram is written as like this. So now here this is the ground state of writing configuration. Now excited state. So in the excited state this electron is moving to the same orbitals, now forming a vacant orbital in 3D. So now this 1 3D, 1 4s and 2 4p electrons, they undergo hybridization, so forming dsp2 hybridization. So now how many ligands are there? There are 4 ligands. So now these 4 empty orbitals are participating in hybridization, that is dsp2 hybridization, making the complexes square planar in nature. So now the hybridization here is dsp2 and shape of the molecule is square planar. You can observe the shape of the molecule as square planar. Here it is pictorial diagram. You can observe nickel Cn, how the Cns are placed and how nickel at the center. You can here see the square planar structure. So you can identify all the electrons in this particular complex as paired. So it is paired, so the magnetic property is diamagnetic in nature. So similarly another square planar structures, copper, the atomic number is written as like this. So here you know the copper atomic configuration is modified, and in order to attain stability, copper modifies its atomic structure by configuration by filling all the D. So 3D 4s1 like this. So copper ion, so -2. So 1s and 1d is minus here. So now this is the atomic orbital electronic structure, and this is how we are writing the ground state. And in the excited state, what is happening? The 3d electron is going to 4p place in the excited state. So now making 1 d orbital, 3d orbital, 1 4s orbital and 2 4p orbitals participating in hybridization, namely dsp2 hybridization. So now 1, 2, 3, 4. So 4 pairs of electrons are donated by ammonia ligand. So now that is how the hybridization here is dsp2, and the structure is square planar, and every all are paired but one unpaired electron is here, and so the magnetic property is paramagnetic in nature. And here we can see the writing pictorial representation, and here is the 3D representation. So now we can see here the octahedral complexes with D2sp3 hybridization. Here this is the example. So this is the example. So now cobalt, the orbital diagram, the ground state here, and ion. So we are removing S, and we are removing the electrons, and here 2 d orbitals, 1 s orbitals and 3 p orbitals are taking part in hybridization, and the hybridization you call it as D2sp3 hybridization. And in the empty orbitals, 6 ammonia is donating 1 pair of electrons each, making this fulfilled. So we can here observe everything is filled. So all the electrons are paired, so the magnetic property is diamagnetic in nature, and the hybridization is D2sp3 hybridization, and so the shape is octahedral shape. So this is how we should write the octahedral pictures, and this is a 3D diagram. So now here we can observe 3D electrons are participating and 4s 4p is participating. So here inner orbital is participating in the bond formation. So these complexes are known as inner orbital complexes or low spin complexes. So now here we can observe here we can see the another example FeCN6. So here also, as usual, the atomic configuration my +3. So we are removing 3 electrons. Here is the orbital diagram, and here is the pictorial diagram we can see here. And after excitation state, here we will get like this, and here 2d orbitals of 3d and 1s and 3p orbitals are joining for hybridization, forming D2sp3 hybridization. So the shape is octahedral. Here you can observe everything paired. So not paired, sorry. See here you can see the unpaired electrons. So the magnetic property is paramagnetic, and this is how we should write the diagram of this octahedral structure. Here you can see some more examples of the same. So here also the inner d orbitals are participating in bond formation. That's why we call this as inner orbital complexes. So here we can see the difference between inner orbital complexes and outer orbital complexes. So here if you take this example, here we can see iron, the atomic structure, atomic configuration, here +3, so -3 electrons. So this is the excited state, and here we can observe 4 s orbitals, 4 p orbitals, 3 p orbitals, and here you can see 2 4d orbitals are participating in bond formation. So here the outer d orbitals are participating in bond formation. That's why the hybridization is called sp3d2 hybridization. And so this complex is called outer orbital complexes, or otherwise called high spin complexes. So here you can observe the structure of the complex. So now to sum up the examples, hybridization and geometry. Here you can have the glance. So if the coordination of number is 2, you can find the hybridization or SP, the structure linear. So 4 sp3 tetrahedral, the examples. So similarly for 4 also dsp2, so you will get square planar and the examples. So similarly for if the coordination number of is 6 d2sp3, so inner shell is involved, so inner orbital complexes, so the shape octahedral. And for same 6 coordination number, you can see the sp3 d2 hybridization, the structure will be octahedral and the outer orbitals are participating, so outer orbital complexes we call. So these are all the different examples for different geometries. So finally, there are certain limitations which VBT theory should be overcome. So these limitations are, it gives only qualitative explanation of structure, bonding and magnetic properties. It fails to explain the quantitative properties, and it is not able to explain the spectra of the complex, and it is not able to explain the colors exhibited by the coordination compounds, and it assumed that every d orbital is having equal energy. It does not consider the splitting of d orbitals energy levels, and the high spin and low spin complexes are not properly explained. It does not give reason for inner and outer orbital complexes. So these are the limitations of valence bond theory, and we will see the rectifications in the next theory. Thank you. Thank you for watching this video. So take home message is believe in yourself. If you like this video, please like and share, and please do subscribe for getting more videos. Thank you. Thank you for watching.